Hey there! In this video, we will see together how I managed to create a MATLAB simulation of the Canadarm2 robotic arm associated with the International Space Station, and how did I perform the inverse and the forward kinematics as well as the forward and the inverse dynamics of the same robot arm. At the beginning, we started by defining the h parameters of the robot. So we define the alpha, which are the joint angles. We define the r, which are the link offsets, or the links offsets, and also the link lengths, which are described by d here. Okay, and after that we created the links, and at the end we just create the robot using the different links here using the Simulink command, and we can simply display the joint based model in specific configuration, which we choose here as a 0 position or 0 configuration. And here we go. As a second step, we perform the forward kinematics, and we mean by that we are going to give as an input to the robotic arm the different joints angle or signals, okay, and we are expecting to see as an output the position of the end effector. Okay, first example, or as a simple example, we just performed a movement between two configurations. So the first configuration is the 0 configuration, which we have all the joints are at 0 degrees, okay, and the final joint angles are as the following, okay, and we want to do this movement in a specific time duration, and which we defined in the line 67, as we can see here. So after that we use the gtrash command to create let's say command signals between these two configurations, and after that we just performed the simulation in the symbolic figure, okay, joint based figure, and after that we just created different time series which are representing the signals to use in order to use them in the Simulink model. Okay, so this is the first simulation. So we are moving from the 0 position to the final position. As well, as I said, we can perform we can see this have the same simulation but in 3D environment using the Simulink. Okay. In the third step, we are performing the inverse kinematics, and we simply mean by that we are looking for the different joint angles by fixing a target position. And as a basic example, we have the following example. Okay, so we created 2 points which are defined as the following, and we have a different points between them. So we use the ctrash command to create the trajectory, and we can see the trajectory together. So it's just a straight line between 2 points. After that we perform the inverse kinematics for each point of that specific trajectory. Okay, and what we can do also is, after performing this inverse kinematics, we can display and we can see together the different joints angle. Okay, so are the signals or the different joint angles that enables, as we said, the robot to reach or to follow that specific trajectory. Okay, and as a final step, we can see the 3D simulation using Simulink. What we can do also is to perform the dynamics analysis, but before doing that we need to define the different dynamics parameters of the different joints, such as the inertia tensor, the damping coefficients, the Coulomb friction, and the rotor inertia. And after defining from new the different links, okay, using all the time the different kinematics parameters, but adding to that the new, or let's say the dynamics parameters, okay, we will create from new the robotic arm using the same command serial link to have now a robot defined, but not only by the kinematics parameters but the dynamics parameters as well. So after defining the dynamics parameters, we can perform the forward dynamics. And we mean by the forward dynamics the fact that we give to the robotic arm a different, let's say, torques to the joints, and we are expecting to see the robotic arm moves. And to do that, we just use the F dynamics, as we can see the command here that we used, and to simplify the computational task, we just use the no friction, let's say, method. And the function, of course, if we are going to simulate the forward dynamics, we need to perform, or we need to give to the robotic arm the different torques, and the different torques are just defined here using the torque function. Okay, so it's just like we are giving a cosine expression that describing the torques, the different torques for the different joints with different amplitude. So we can run the simulation. So first we are computing the torques. After that, we can display these torques. And at the end, we can run the simulation. In the same way that we did with the inverse kinematics, we have the same methodology here in the inverse dynamics. So all the time we have the specific position that we want to reach, and we want to know what are the necessary torques that we need to give to the robotic arm in order to reach or to follow that specific trajectory. Okay, so here I'm using all the time the same trajectory, and I'm computing for each position, or for in that specific trajectory, the necessary torques that enables the robot to reach that specific position in the trajectory. Okay, so here I'm computing the torques, and this is the different torques that enables the robot to follow, as we said, the trajectory. Okay.